Hey there, Calc folks, back here with another video in our study of the derivative. And so far we've introduced the definition of the derivative. We've seen some of its application in finding slope of the tangent line. And we've developed some fundamental rules, four fundamental rules: the constant rule of derivatives, the power rule for derivatives, the constant multiple rule, and the sum and difference rule for derivatives. We've developed these generic rules for differentiation, right, using our definition of the derivative, where we want to continue now looking at some more advanced situations for calculations of derivatives, right? What we've calculated so far in terms of our rules, what we've developed so far in terms of our rules, has probably felt rather intuitive, right? Especially with the distribution of the derivative across sums and differences, the factoring out of a constant multiple, right? Those probably feel very intuitive in their process. Well, what we're going to be looking at are some more advanced rules where the rule itself may not be so what we might think it is, right? Might not just be what we would think would develop from some sort of intuition. Again, though, what we are going to see are these rules developing from applying the definition, right? The definition of a derivative to some generic situations, right? But we are going to be developing some rather advanced calculations. All right, let me bring this up. Again, here we're going to be looking at advanced rules for differentiation. We're going to be looking at what's called the product, the quotient, and chain rules. Product and quotient kind of makes sense, right? We've kind of worked with products and we've worked with quotients. As for chain rule, that's a rule that's going to allow us to find the derivative for the case of having a composition of two functions. Which, with numbers, we don't really compose numbers together. We can add them, subtract them, multiply them, and divide them. But we really don't compose two numbers together. However, with functions, we can do those things: add, subtract, multiply, and divide, but we can also compose them with each other. So we're going to look at an advanced rule for composition of two functions, which is going to be known as chain rule. Now, I do break this down into just the product rule in this video, and I will follow up with the quotient and the chain rule in the next two videos, right? I just want to try to keep it brief. But let's talk a little bit about product rule here, right? And I say, consider finding the derivative of y with respect to x, where y, we might say, is this factored polynomial. All right? We might think of y being this factored polynomial involving this linear factor 3x minus 5 and this factor 4x squared minus x plus 5. Right? We could consider evaluating the derivative of this factored polynomial by actually going about expanding that polynomial and then going back and applying our first four fundamental rules for the derivative to determine that value of dy dx. However, there is another approach we could consider, right, involving what we would call the product rule, because what we are seeing here on the right-hand side of our value for y is the product of two separate functions. We have the product of 3x minus 5 with the quadratic 4x squared minus x plus 5. Right? Instead of expanding out that product, right, we could consider calculating the derivative with just the factors of that product. Right? The 3x minus 5 and that quadratic 4x squared minus x plus 5. Right? We can use what we call the product rule for differentiation. Now, what is the product rule? Let me bring it up here. It is, like I said, not quite that intuitive. Right? It isn't simply a distribution of differentiation. You'll notice that when you look at the rule here. We're going to assume f and g are two differentiable functions. We're going to be working with two differentiable functions, one function f and the other function g. Where here we're going to be looking at taking the product of f with g, looking at f of x times g of x, and finding the derivative of that statement with respect to x. And what we see as the result is over there on the right-hand side, this statement seen here, where what we say the derivative with respect to x for f of x times g of x is it is the first derivative of f times function g. Right? That's this first term, the first derivative of f times function g, plus, there is a summation involved in the product rule where you are summing these two products, where the second term is made up of the product of f of x times what would be the first derivative of g. Right? That's known as the product rule. The derivative with respect to x for f times g is f prime times g plus f times g prime, is how we can sometimes say that rather quickly. Right? We might say here in a shorthand, right, we might say something like the derivative with respect to x for f times g is equal to f prime times g plus f times g prime. Right? We could express that same idea in very much a shorthand statement like such. Right? Where we understand f and g and f prime and g prime are just functions of x. Right? So this is called the product rule for differentiation. If we notice above, for y equals 3x minus 5 times 4x squared minus x plus 5, we might think of f as being this linear function 3x minus 5, and we might think of it as g as being this quadratic function 4x squared minus x plus 5. Well, those would define the f of x and the g of x I would see as components in each of the terms for the result on the right-hand side, where what I would need to find also for f and g would be their first derivatives. I would need the first derivative of f to multiply by my g, and I would need my first derivative of g to multiply by my f. Again, if this is f, the first derivative of that should be pretty quick and easy to find, especially with a little practice. These are just linear and quadratic forms, or just polynomial forms, where we can find their derivatives using some of the fundamental rules individually. Let's set this up. I do set that up down below here. Right. For y equals the product of these two functions, the linear with the quadratic, dy dx, the derivative of y with respect to x, is the derivative with respect to x for the product of 3x minus 5 with 4x squared minus x plus 5. It can be thought of as the derivative with respect to x for f of x times g of x. Right? Where in this setup of the product rule, we are defining f and x to be the functions 3x minus 5 and 4x squared minus x plus 5, respectively, for f and g. Right? We're going to think of this as being f and this being g. Now from the setup, I'm going to need the derivative of f, and I'm going to need the derivative of g. So you'll see that's the next bit that comes into our calculation here. This setup implies that when we think about the first derivative of f, well, that's going to be the derivative with respect to x for 3x minus 5, where if you just follow your fundamental rules, that derivative will distribute across the difference. And the derivative of 3x will be simply 3 minus the derivative of 5. Well, the derivative of 5 is 0. So the end result here for f prime of x is just the value of 3. Right. Again, we might show that that is going to equal the derivative with respect to x for what we might say is 3 times x. So we'll bring the 3 out as a constant multiple minus the derivative with respect to x for what's going to be the constant 5. And what this is going to result in is 3 times the quantity 1, because the derivative of x with respect to x is 1, minus nothing. Because the derivative with respect to x for 5 is nothing. Right? We could develop our f prime of x, right, using just some of those fundamental rules applied in this manner. And that does lead us to this value equaling 3. Right? I'm going to take that out just for the sake of space. Similarly, for g prime, the derivative with respect to x for this quadratic can be handled similarly. Right? When we think about its result, maybe I'll bring this down below just for the sake of space, and I'll erase it. It can be thought of as the derivative with respect to x, where for the first term, 4 would be a constant multiple. We would factor that out, and we'd be left with the derivative with respect to x for x squared, minus the derivative with respect to x for x, plus the derivative with respect to x for 5. And yeah, 4 times the derivative of x squared following the power rule becomes 2x. Minus the derivative of just x with respect to x, that would just be 1, plus the derivative of x with respect, or the derivative of 5 with respect to x, which would be a constant, would just add on nothing. So when we simplify this, 4 times 2x gives us 8x minus this value of 1. And that's where we get that result from. Again, just applying our fundamental rules. Now with these 4 parts, right, it is just going to be f prime times g plus f times g prime. That is our product rule. So for product rule, right, as we said, it's going to be f prime times g plus f times g prime. So if we bring those results up for our specific case, where are they? There they are. Right. Remember, f prime was simply 3 times g of x. Well, g of x was that quadratic 4x squared minus x plus 5. We're going to add that to what was f. Again, remember, f was 3x minus 5. And we're going to multiply that by g prime, which is 8x minus 1, right? The derivative of this quadratic. We found that right above here. Now, if we expand the 3, distribute it, we get 12x squared minus 3x plus 15. If we expand this product of 2 binomials, the 3x minus 5 times the 8x minus 1, that will become 24x squared minus 43x plus 5. Where if we combine like terms with that, the 12x squared plus the 24x squared is 36x squared, minus 3x minus 43x. Oop, I have an error there, don't I? That should give us 46x. And then the 15 plus the 5 is going to result in 20. Oh, glad I go through these because I am looking for those little errors. And that is our derivative. Thus, for the product of these two quantities, the linear with this quadratic, the derivative of y with respect to x is 36x squared minus 43x plus 20. And again, we have to change that, right, to 46. Right? And we found that using product rule. We took the derivative of this first factor, that was 3. It was multiplied by our second factor, the 4x squared minus x plus 5. We added that to our first factor, which was 3x minus 5, times what would be this factor, which was the derivative of our second factor, 4x squared minus x plus 5. Once expressed as the result of the product rule, we can then just simplify by expanding and adding together like terms, making sure to do it for every term. All right. That's a little bit of product rule, folks. As we go further into our study and we're introduced to more derivative rules for different function types, we'll see product rule work itself back into our work. I promise. All right. What we should probably spend the last moments with is a little bit of proof. Here's proof of the product rule. What we start by doing is declaring the product of f and g as just the value for the output for one function we refer to as capital H of x. Right? We consider letting h of x equal what's the product of f and g, f times g at x. Which implies then, if I'm interested in the derivative given by the product rule, I'm interested in the derivative of h prime of x, or h of x, the value we would refer to as h prime of x. Right? H prime of x then would be the derivative with respect to x for f of x times g of x, if h is the product of f with g. Right, what we're denoting right here. So if we think about applying the rule to h, right, or be careful there, apply the definition of the derivative to h, then h prime is going to be the limit of little h, as little h heads to 0, for what is the ratio of big H at x plus h minus big H at x, all divided by h. Where if we say that specific with respect to f and g, we can state that specifically with respect to f and g is this. Right? F at x plus h times g at x plus h represents the capital H at x plus h. And then we're going to take away from that h of x, which is just f of x times g of x. And all that's going to be divided by h. All right? So we're starting to see a little bit more of an explicit case now start to develop involving functions f and g. Now where we go from here, folks, is a bit of a trick. Just a little bit of a mathematical trick here. Let me bring it up and show you what I mean. Where we go in the next two statements is into this. Where you can see in the numerator above, right, from what we had before I brought these items into view, this statement here I've highlighted. I still have that statement down below here, where here is our first term, f at x plus h times g at x plus h. And here's our second term, minus the f of x times g of x. What I have included between the two terms, though, is this quantity I'm highlighting right here. The quantity given by negative f of x times g at x plus h plus f of x times the quantity g at x plus h. Where if I note, I'm adding and subtracting the same quantity inside that numerator, and really all I'm adding in there, if I highlighted it, I'm really just adding in 0, nothing. But I'm adding in 0, nothing, in the form of negative f times g at x plus h plus f at g at x plus h. Now I write it that way because what I'm able to do now in our next step, and I probably should maybe highlight this. Let me go ahead and bring this down. One more step. We are going to group those statements together, and we are going to group those statements together. Right? And from this group seen right here, perhaps I should show it in the next step too. We're going to factor out from each of these terms in this first group that g at x plus h. It can factor out of those two terms, and we will factor that out. So we'll end up with g at x plus h times this group, f of x plus h minus f of x, plus, and then here, we can factor out this common factor of f of x. And it would factor itself out here of both terms. And it would leave behind in the group g at x plus h minus g at x. Where now if I break apart these two terms separated by this addition over a common denominator of h, and I pull out those common factors of f and g, right, I can actually express that limit statement as this, where that limit, right, can be applied as such. And now it's going to distribute itself across the sum. And when it distributes itself across the sum, well, it'll then distribute itself into the product of each term. Right? The factor, right? It'll apply itself to this factor, and it'll apply itself to this factor once it distributes itself across that sum. It'll apply itself to that factor, and it'll apply itself to this factor. So you'll end up with the limit of the first factor from the first term times the limit of the second factor from the first term, added to the limit of the first factor from the second term times the limit of the second factor from the second term. Now notice this limit for the first factor from the first term is just defining, by the definition of the derivative, the value we would call f prime of x. And by the definition, this limit back here, the very last factor in the second term, the second factor in the second term, it's defining, by the definition of the derivative, the value we would call g prime of x. So here I have g prime highlighted, and up front here I have f prime highlighted. Now those are being multiplied by this statement here, whereas as h goes to 0, this is just going to become g of x. And when h heads to 0 in f of x, well, there's no, that's a constant with respect to h. So it's just going to also be just the value f of x. And when we think about these values, this is the result we see given by the product rule. As we said, this limit is f prime. That's going to be times by this limit where h becomes 0 through substitution, and you're left with just g at x. All right. That's all added to the limit of f of x as h heads to 0, which is just going to be f of x. It doesn't involve an h, it's more like a constant behavior, times the limit of this statement involving g, which by definition of the definite integral of the derivative is our result g prime of x. And that's the result we have for product rule. All right, I Do I say that below here? No, I probably should say that. Let me go back up and say something like so. The derivative with respect to x for f of x, f4 dot g of x is equal to f prime at x times g at x plus f of x times g prime at x. And that's the result we have from our product rule. What you see here, folks, is the proof. I always like to try to give a little proof for where these rules come from. Where did this less than intuitive rule come from? Why is it f prime times g plus f times g prime? Well, that f prime times g plus f times g prime is a result of the statement above, which is itself a result of applying the algebra above to what was set up originally as a function h, capital H, right? Where capital H was thought of as the product of two functions f and g. There's the proof of our power, or our product rule. Little trick in here, right, is when we add in the 0 right here. We don't add in 0 as we understand it, though, or see 0. We add it in by adding in these two opposite quantities, which allows us to break it apart into the two statements that we finish with. These two terms here, this first term added to this second term. Right. So, folks, that is product rule. We're going to come back, look a little bit at next what we call quotient rule. And like product rule, it is also going to not be quite as intuitive as we would expect. There are going to be some nuance to the formula known as quotient rule that we're going to look at in both practice and in proof. All right, folks. So that is where we're heading. Again, I'm going to break these videos up because, yeah, even though we looked at just one calculation here, that took almost 30 minutes. So I'll be back in my next video with quotient rule, and then the video after that we'll look into a little bit of chain rule. And what we're developing here are some advanced rules, folks. All right? Some advanced derivative rules. So with that said, I'll stop, and I will see you in the next video.